Hi there. I made a little video segment for you to look at some of the important points related to projectile motion. Now, projectile motion is a special case of two-dimensional motion. So if you've seen a recent treatment of two-dimensional motion, just know that we usually don't use the real formal approach when we do projectiles. They're kind of a class of their own. Pretty typical in a mechanics class that you're doing projectiles, and they tend to be done the same way. So things might just look a little different than some of the other problems in this chapter. So I'm just going to use probably one of the more complex situations that we could have, and I figure that if you can see what happens in these complex situations, you can probably simplify it for the other situations that you might see. So I'm going to use the example of something that is not symmetrical. So it's not going to start on the ground and end on the ground like a soccer ball typically would, or maybe somebody's throwing a football. I'm going to start it up on a little cliff, and also we're going to be looking at not a horizontally thrown object, but an object thrown with a little bit of an angle involved. So first, let's just draw a good representation of what's happening here. So I'll draw a little cliff like this, and this is just a rough sketch. Maybe we'll have a ball here that gets thrown, and I'll give it some numbers here. Perhaps let's use 15 meters per second, and let's say it's launched. We typically give it from the horizontal at an angle of 65 degrees from the horizontal. And so what's going to happen here? Well, that's the initial launch, but doesn't continue along that path because gravity starts working on it. So if we follow the path, the projectile going to make a path something like that. And again, I'm just hand drawing this. So we've got a collision point there, and maybe part of what we'll do later is figure out how far it lands from there. So questions we might typically ask that I'll show you here is maybe how high does it go? How long does it take to land? How far over does it go till it lands? And in order to do any of that, we have to approach this from the standpoint of components. You cannot really deal with this 15 meters per second and 65 degrees because this is the only point in the path of the projectile that it has that particular velocity. Gravity is going to start reducing the vertical motion of this until at the time at the peak, it's going to be completely out of its vertical motion, and then it'll start picking up some downward motion after that. But meanwhile, it's moving rightward the whole time. So we refer to this in the physics lingo as the independence of the two perpendicular directions. That means despite the fact that it's changing its vertical motion, slowing down and then speeding up, it's not going to change its horizontal motion at all. Now we're assuming that we have no significant drag force from the air, and so that's all kind of taken into account. In real situations, you do have to account for that. We're not ready for that yet. So because we have to deal with one component at a time, we have to first take the initial velocity and break it into components. So everything in projectiles must be done with components. So I think you should have been through this part before. I'm going to draw the components here. I draw it as far up as this vector goes up, and I draw it over as far as this vector goes over. So I previously calculated these. I would use the sine of 65 to get the vertical component, and that ends up 13.6 meters per second. And I would use the cosine of 65 to get the horizontal component, and that's 6.33 meters per second. Try to keep a couple extra digits as I do these preliminary steps so I don't end up rounding multiple times to get my final answers. So let's start with this. How long does it take to reach the peak? So if we think of this now, instead of a 15 meter per second launch, we're going to think of this as something that is thrown upwards at 13.6 meters per second, while also thrown sideways at 6.3 meters per second. So which of those is going to affect the amount of time it takes to get to the peak? Well, I hope you see, because gravity is going to be responsible for slowing it down, and gravity is only a vertical phenomenon, that it's only the vertical motion that determines how long that takes. So if we want to write it out formally, I'll write time to the peak I think about what I know at the peak. Up here is where the vertical velocity, I'll call that v sub y, is momentarily 0. That's, of course, why it's the peak. It stopped right there. So I've got a relationship that says that my vertical velocity is equal to my initial vertical velocity plus the vertical acceleration times the time. So this is a very typical kinematics equation. I put y's in there because when we do projectile problems, we got to keep it straight. Are we dealing with y or are we dealing with x? And I don't want to ever mix those things up. So what I know here is my vertical velocity will go to 0. I've got 13.6 meters per second for my initial vertical velocity, and I've got an acceleration of negative or downward 9.80 meters per second squared. So the only thing missing here is t. So maybe writing it out formally, it looks a little better. This would be negative v naught y divided by a sub y. So that's the opposite of 13.6 meters per second divided by a negative 9.80 meters per second squared. And that'll give me about 1.4 seconds or so. Now, as we do with any kinematics, we've got to be very mindful of directions. So because my initial velocity was up, but my acceleration was down, I have to give those different signs when I plug it into the math equation. So that's the time to the peak. Now, how about the height? What I'm going to find is the height above the initial launch level. And I'm going to throw a number in here. Maybe this is a 5-meter high cliff where I was launching from. And I want to find the height above the ground when it reaches its peak. So if I can just find out how high above this initial launching point it is, then I can just add the 5 meters to that. Well, if you think about, again, what we know the initial vertical velocity. We know that it's accelerating. We know how long it's in the air now that we found it. So we've got an equation that says that the vertical displacement is equal to the initial vertical velocity times the time in the air. Now that would be, if we stop there, that would be a great equation for steady motion. But of course, this is accelerated motion. It's not going the same speed. It's going to slow down because of gravity. And so this second term here actually accounts for what gravity does during that same amount of time, 1/2 at squared. So again, I have all the numbers here. So dy, I'll plug in 13.6 meters per second for my initial velocity, time of 1.4 seconds, plus 1/2. Again, watch out. I got to use a negative on my acceleration in the same amount of time here. And I've calculated this previously, 9.44 meters. Now that's a bunch above the launch level. I guess I need to be specific. If I add 5 meters to this, that would be a height above the ground of 14.44 meters. So I'm just going to write above the ground. I don't want anything to be ambiguous here, and it's a good idea. A good physics student would write as many words as they write equations and numbers just to clarify what you're doing and what every number represents. This is, you notice here, time to peak and height. I do that just to make it very clear in my instruction, and you as a student can make it clear in your presentation also. So what else could we do here? I think I'm going to turn the page because I've got 2 more things I want to do, and I don't think I'm going to have room on that page. So what if we want to find the time to land? The time to land, if you think about what we know, of course we still know the initial vertical velocity, v naught y. We of course know the vertical acceleration because that's gravity's acceleration. And we would know the displacement. I'm going to call that dy. Now you can use dy. In my class we sometimes use delta y. I'm just using this because it's a little simpler. You know, that's from the initial launch level down to the ground is 5 meters downward. So, you know, we can use 13.6 meters per second We can use negative 9.8 for the acceleration, and negative 5, because that's also a downward quantity when you consider the vector direction. And so we've got an equation that relates all this with time. And what equation is that? Well, it's the same equation we used before. dy is v naught yt plus 1/2 at squared. So I think I'm going to spare you the mechanics of actually plugging this in, because the video is going to go pretty long. But if I put these values in, notice I'm going to have a t and a t squared. That's beyond an algebra solution. You're now having to do the quadratic formula. When I say algebra solution, I mean you can't just do a little simple algebra and solve for t. So you're going to have to use the quadratic formula. That can get a little messy, but it's something at this level you should have done before. And if you do that, you will get t is 3.1 seconds. Again, I'm not showing all the work for that. But the reason I want to skip that part is to show you another strategy. You remember that we found it takes about 1.4 seconds just to get up to the peak. Well, it might be just as simple to calculate how much additional time it takes to get to the peak down to the ground again. So again, I'll label this time to go from peak to ground. See, we still have the initial vertical velocity, but notice this time it is not 13.6. We're not starting at the initial point. We're starting from the maximum height where the velocity at that moment was 0. That's a clever little trick, because we love zeros in equations. They tend to simplify things. We still have the acceleration due to gravity, and we have our vertical displacement now, which would be the entire 14.44 meters, and that's downward, so that would be negative. I guess I'll put in negative 9.8 here. And so we can use this equation now, but the middle term is going to become 0. So that's quite handy. And if you plug those numbers in there, you will get, what are you going to get? Well, I can tell you, you're going to get 3.1 minus about the 1.4, so what would that be? About 1.7 seconds. You can trust me on that. Actually, I did it on my calculator earlier and make sure it's still there. Yeah, about 1.7 seconds. So when we add that to the time to get to the peak, that's 1.4 plus 1.7 seconds. There's another way to get the 3.1 seconds. So just a different strategy. And there's no one right way to do that. You can do whatever way you're comfortable. Final thing I want to do is to show how long, or how far rather, horizontally. So just looking at my picture again, I drew the projectile landing out here somewhere. So what we're finding is from the launching point to the landing point, how far will that have gone? And this is the first time and only time in this problem where I'm going to use this horizontal velocity. I mentioned before the independence of perpendicular vectors. It doesn't matter the fact that this is going up and down. It's still maintaining the same 6.33 meters per second rightward the entire time it's in the air. Students have a hard time believing that's true. They want to think that if it's changing its vertical motion, that must somehow change its horizontal. But demonstration can show that that isn't true. So this is finding now what we'll call a dx. See, I'm using the subscript x because we're now dealing with horizontal motion. And the beauty of this is there's no acceleration. We're only accelerating due to gravity, not any horizontal effects if we ignore the effect of air drag and wind. So we can go to a much simpler form of a displacement equation. It's just the steady horizontal velocity multiplied by the amount of time it's in the air. So we know it was moving at 6.33 meters per second. We just determined it was in the air 3.1 seconds, and that gives us total displacement of about 19.6 or so. You might find some rounding differences. I'm using some numbers that I calculated previously. So that's how we would do the horizontal motion. So I think we've seen just about everything you'd see in a typical projectile problem. And I know 15 minutes is a long time. You probably are not going to see all of these in every problem, but I think I've shown you enough strategies that hopefully you can get through just about everything you're going to see. So I'll leave it here. Good luck.